Howdy howdy. This should be the last video in the Vectorized Implied Volatility series. I think I mentioned in previous videos that some time ago I was doing studies, data analysis on volatility products, and I had purchased a large quantity of options data on an underlying called UVXY. UVXY is basically a doubly leveraged VIX product. It's relatively illiquid. It's not horrible, but it's really not the most liquid thing out there. And since the volatility of volatility is typically, say, 60, 70, 80, even 90%, the volatility of UVXY is twice that. So you're looking at volatilities in the range of 120 to, I don't know, 180, 200 even sometimes. So I think this was a good test bed just for showing how to calculate these sorts of things in a vectorized sort of way, because there's tons and tons of data points which are going to give you bad results. So I think I got it mostly there. I think it's good enough that I'm just going to kind of present it here and then tie a bow on this series of videos. I think there may be like 10 to 20 points out of thousands that the algorithm fails to actually produce a decent result for. So let's just get started. Okay, for our imports, we're just going to use the standard things. The only thing different here is I'm importing some time delta stuff so that we could take our raw options price data, which has dates, and then convert those date differences into days until expiration. So I'm going to import the data, import my raw data. These data are for UVXY, as I mentioned in the introduction, which is the volatility product that I purchased these data files a couple years ago. So it's a rather large comma-separated value file, so pd.read CSV. The file is simply called uvxy.csv. Let's print out the size of it. So print data.shape. So it's a pretty big file. It has well over 500,000 lines. Now Pandas imports the dates in this case as string. So I'm just going to convert those two columns to date time, and let's just print out. Let me just comment out this, and let's just print out the first few lines of this. So print data.head. So this is how the data file is organized. Stock symbol, all of them are going to be UVXY, the particular exchange, trade date, adjusted stock, close. UVXY has gone through several splits, so we're going to prune this down just to avoid having to undo all the reverse splits. Yeah, so it's pretty straightforward. Let's see, option symbol is not relevant for us. Expiration date, strike, whether it's a call or a put, so we could separate out. We'll probably test all the code with call, so we'll probably do some splitting on whether it's a call or put. These are all American style options, and then the actual prices. So to avoid some clutter, let's go back here and comment that out. Okay. So I am not going to deal, as I said, with the reverse split, so I'm just going to chop off the data from the last reverse split that was in this data file, which happens to be here. And I'm also going to get rid of super low volume options and things with zero bid. So let's just see how much we chop this down by. Quite a bit. We only have like a little under 4,000 option contracts to deal with now. And for bookkeeping purposes, I am going to split these into both calls and puts. So I'm going to do this, and I'm going to do put is equal to what? DF, and we're going to do DF call put. And that is equal to P. Okay. And so now I'm going to separate out all the information we need, and I'm going to separate them into NumPy vectors doing this. So here's our time vectors for the calls, our strike prices for the calls, the price at this particular time, risk-free rate, I'm taking it to be 1%, and the ask and bid prices, and I'm going to do the same thing for the puts. And there's a typo here, isn't there? This should be R put. I know R is a constant, but just for convenience, I'm going to define it both for calls and puts. So run that. Okay. Issue? Keyword T. I probably skipped defining my time. So let's come up here. Yeah, I did. Let's do this. So we're defining our time based on our expirations. We're just changing it into fractions of a year. So let me rerun that cell, rerun that cell, rerun that. Now we're good. Okay, in my test code, I actually defined mid prices for the calls and puts. I don't think I'm going to do that here because there are some issues that are going to turn up. So I'm just going to use basically the ask price for the option rather than the mid price. So what I'm going to do now is just import our Black-Scholes model from previous videos. So Black-Scholes model, and we'll make this markdown. So okay, let's paste them in, make sure that runs. Good. Now, I think I mentioned this in other videos, but when I first did this code quite a while ago, I used functions here, the square root, for example, and the logs pulled in from the math package in Python. So what we're doing here is we're just using solely NumPy functions for the logs and the square root. See np.exp here. This has the advantage that we could do this in a vectorized way now. As long as we pass in objects that are the same shape, this code will evaluate this, for example, the call price here as a but in a vectorized element-wise manner. So what we have here, we have call price, put price. We have the actual objective functions, which we're going to actually find the roots of for call price, put price. And we also have the calculate vega, which is the derivative of the option price with respect to volatility. Now, okay, I think I'm going to put this below these functions here. One potential issue we saw in the previous videos that this technique might fail is if you're trying to find the root of a function that does not have a root. Now, these data, as I said, are actual stock market data, but I don't know about things like stale quotes or whatever. So there are definitely some prices in here which are going to screw things up. So I'm going to create a function that's just going to call find no roots, and it's just going to return the indices of those particular the indices that cause a problem. So let's rerun this, and actually let's just call this function now and see what how things are. So okay, so I just realized something happened to my audio, so I just deleted a large portion of this, and I'm not going to kind of re-talk through most of this code because we've done it before. But what I did is I took that function I just mentioned and I ran it. So we do have some points for which the volatility, there is no root. So let me just rerun this code to show you that. Run. So we have a bunch of naughty points. So basically I'm just going to delete them from the array. And I did not say how this function worked, but basically we know that volatility is a positive number that is, it's an always increasing, so it has a positive slope. So if we were to plug in the value of our objective function at sigma equals 0, you should get a negative number. So this code just looks for values where the objective function at 0 is 0 or positive and returns those indices. And you see we get a divide by 0 error here, or warning here. And before going on to the rest of this, I did make a comment about knowing how your code or your library works. So obviously 5 divided by 0 is going to give you a problem, divide by 0 error. But what about np.array? We'll make this a NumPy, part of a NumPy element. Okay, so it treats it a little bit differently. It takes essentially the limit as this denominator goes to 0 from the positive side. So what if we do np.array not mp.array, but let's go norm CDF, which we make use of in our Black-Scholes model, the distribution function, and we do 5 divided by 0. Okay, that gives us an error. But what about what happens if we pass in this infinity, this mp.array? So that is fine, because we do know that this function goes to 1 as the argument goes to infinity. So it's just a thing to watch out for, because if you use a different library, it might be handled different ways. Sometimes you can find this in the documentation, sometimes you can't. And if you code these functions by hand, you might have to account for these type of things. So let me get rid of that, and let's go back to where were we here? Let me comment this out. Because we chopped a bunch of stuff off, let me just rerun these cells. Okay. This is our Newton's method. I'm not going to talk too much about how it works because we've done it tons of times before. The main difference that I did not talk about is I changed the way the tolerances are calculated. So if a single value is passed in, it uses our old technique. It basically looks at the percent change from iteration to iteration. Again, this can cause problems if the old value was 0, you get divided by 0. In the case of the vectorized code, what I did is I took the infinity norm of the result minus the old result vector. So what this essentially does, it takes the absolute value of this r minus old r array and returns the maximum value. It's just a compact way of doing that. So let me just make sure this is pulled in properly. And since we chopped elements off of our arguments arrays, I kind of rebuilt the arrays, and we called our Newton's method function. So let's run that. And as you could have already seen, there's a bunch of warnings here. Now, and so down here I ran some basic diagnostics. I looked for values where the volatility turned out to be infinity, and indeed there were, how many? 17 of those. And values where we got not a number, there were none of those, and likewise where we got a negative value for the volatility. So there are basically 17 problem children here. Not a big deal. I'm not going to try to find a way to fix these. I'll just look at one of this. I'll look at the first element of I is equal to IND1, 0. So what did I do here? It should not be, oh, I didn't take it out of the array, so IND0, 0. Something just seems odd here. Print IND0, 17. There's only one problem child. Let me just rerun everything to make sure we didn't overwrite something. Apparently there's only one problem child. Okay, so let's look at element 17. So the stock price was what? Oh, come on. What the hell? Print s call I. So $75 stock price. Strike price was 65. And let's multiply this by 365 to put it into days. I did something a little silly here. I had just kind of copied and pasted this, and what I wanted here was basically this. So, well, now I have to rerun everything, damn it. So I thought these numbers were a little too good to be true. There's only one that actually blows up to infinity, but there are a handful of nada numbers. So let's come down here and delete ind1. Can I do this? np.hcat ind1, ind2, and I think these need to be wrapped in parentheses. Run. My normal typing abilities plus my computer's really been acting up today. It's caused a lot of problems. Okay, so I took care of one of the browser problems, and this is stack, not cat, so it's h stack. Okay, I made one more change up here where I set, I'm just looking for volatility greater than 20, so extremely large volatilities that don't really come out as infinities here, and then chop them down, and you can see this is our final result for all those almost 2,000 call options. So this generally works pretty well. You know, volatilities between say 150 and 200%. Whether these are convergence issues like this one that goes up to, what is this, 12. It's probably a convergence issue, but yeah, I'm obviously not functioning at 100% today. You could tell by all the mistakes I've made. So I'm just going to call it quits, and I'll clean up the notebook and do the uploads and whatever. So if there are any questions, feel free to ask, but I'm kind of sick of this topic, and you know, what you could do is just pull out some of these naughty points and run it through a bisection method or something like that to fix it. You could also look at constrained versions of Newton's method. There are various optimizations that do that. So yeah, I'm going to call it quits here. Okay, so I lied. I'm going to do a little bit more here. What I did here is this is the same plot we just saw, but I just rescaled the axes a little bit here. What I wanted to do was solve this in Matlab, which has basically a lot of canned routines for this type of thing. Come on. So here's the code I came up with. What I did is I just exported our processed data from the UVXY thing that came out of Python. Same idea here. I have the call price. I have a function that solves for that using the fsolve routine. And just for speed's sake, I calculate the Jacobian because in this case it's pretty easy to do. And run the code. It works reasonably well. As you can see from this test run, it does tend to get to the maximum number of iterations. I played with it, bumping up the total number of iterations, and it doesn't really get much better than this. So we'll call it good enough. Because there are a lot of iterations, it takes a bit of time to run, but it's not that bad. So this is the result we get. You see it's about the same as NumPy here. It does a little bit better of a job. You notice NumPy has these spikes here, these you know, where we got poor results, but other than that, it's more or less the same. So Matlab does a little bit better job. It does have one case where we get a negative number, but other than that, it seems to do a decent job. So what's going on here is there's probably no solutions to these particular values for the reasons we've discussed in the previous video. You're at a point on that curve where the slope is essentially 0 or something like that. But I just wanted to run it through Matlab to see what type of results we could get. And now this time for real, I will call it quits. Cool. So that's going to be basically it for this series. As I said before, I'm kind of more than a little bit sick of the topic. When I did it originally, that first video over a year ago at this point, it was just intended as a means to combine a couple things that I really like. I enjoy these types of applied math problems, and I like trading and finance. So it was just a good topic to do a video on. I never assumed it was going to turn into such a large portion of this channel at this point. I think something like 1/5 of the videos touch on it in some regards. So yeah, unless there are any burning questions on the topic, I'm going to try to put it to bed and move on to different topics. So yeah, until next time, see ya.